Hello, everyone. Come on in. Anybody have any questions while we're waiting for others to come in? Got about 9 of you in here now. 10, sorry.
Is the chapter 44 homework going to be homework or is it extra credit?
Yeah, I'm going to go ahead and consider it to be homework. I might later change it to extra credit, but for right now, treat it like it's full homework.
And is there a conceptual section with it? Because it doesn't look like
that's not
there is.
There should be. I will put that up, and I will make that extra credit definitely, since I didn't have it up for you already.
I just got my mic or my speakers working. What is homework?
The chapter 44 stuff.
Yeah, 43 and 44.
Okay, so we need to complete up to 44.
Yeah, that's the ones that I'm counting as full credit. I might change the 44 to extra credit later, but I would go ahead and bank on it being credit.
Okay, sounds good. Thank you.
No problem. And I think with your help, I finally got all the actual practice tests working properly. Let me look at I'm checking out chapter 44 conceptual questions right now, plus I'm grinding my processor to a halt. Yeah, it seems I do not have a 44 concept. So I will definitely have to make one, but like I said, I'm going to make that and have it extra credit for you guys. I just don't like to not give you a concept chapter so that or homework so that you can better understand the concept. So I'll work on that and give you something. Anybody else have any questions?
Just curious, how many questions is the final going to be?
I think yours, I ended up doing 45 really quick questions. So it's all encompassing. It covers all the material. But
in the practice is only 5 questions though.
yeah. Basically, because I didn't want you to get overwhelmed with more than normal. And also the ones that I'm choosing, they will appear. They're part of that bank that you're using for the practice test, but the ones I chose are on the easier side. And it allowed me to get, a number 45 questions. If, like I said, I think that's what the number was. By getting 45 questions, that allows you to screw up several and still get a good grade. And to give you an idea, I used the same size test, not in the summer, but in the spring of last year, I used the same size test. And I think the longest anyone took was 70 minutes, 1 hour and 10. So it should be plenty of time for you. Don't forget, your test will start 1 week from today. You will be able to start it as early as we start at 12:30, so it'll be as early as 11:30. But you definitely need to start it somewhere between 11:30 and 12:30, because if you start it late, you won't be allowed the full 2 hours and 10 minutes.
I saw that the testing center midterm, the time for it was like from 9:30 to 11 or something.
Yeah, I wasn't sure if they would be able to fit you in, so I gave it a little leeway there, and I changed some of the questions on that one, just to so there wouldn't be too much overlap in case you took it early and then talked to someone. But if you take it at the regular time, that would be preferred. But I wanted to give you that freedom in case something went wrong or they didn't have an opening at that time or whatever.
Are there going to be like any concept questions on the final? Because on the midterm, all of it was just
problems.
All of it just problems.
If I remember correctly, I think I had 3 or 4 concept questions on there, but not many.
Okay, all right.
Yeah. Make sure you read chapter 20. Reading it gives you some of the concepts that I mentioned, but it might not have sunk in your head from me just telling you it. So, remember we covered the first law of thermodynamics, the second law of thermodynamics, but I pretty much just wanted you to make sure you knew numerous versions of the second law of thermodynamics. And I didn't even mention that part. There was a 0th law of thermodynamics that I didn't mention in class, but if you do your reading, you'll know about it.
We never did thermodynamics.
Oh, sorry, I'm looking at 241. That's my fault. And in fact, that might be y'all might be doing 20 questions, and I was thinking I was in 242. Sorry about that.
I just looked
Scared
at
you, didn't I?
22.
Let me check that real quick. I will answer your question immediately.
Well, I'm down to clown with untested material. Or
Kill something. I think, yeah, that's what's killing me. I didn't realize Zoom was still converting. That's why we're getting everything coming in and out. So I think I fixed that now. Yeah, here's what I did with your test. It turns out your test has 14 questions, but you're only supposed to submit 11. Or excuse me, 12, sorry about that. And it says this is your final exam for physics 241. There are 14 questions, but you're supposed to only complete 12. Work all of them if you like, but only submit answers for 12 of them, or your 12 worst will be graded. Okay, so that's the deal with that. Make sure y'all don't make that mistake, everybody. Everybody hear me? Do not.
Can you repeat that real quick?
What's that?
Would you mind repeating that real quick? Which
Yes.
is that exam or the?
This is your final exam. It says, this is your final exam for physics 241. There are 14 questions, but you are supposed to only complete 12. Work all of them if you like, but only submit an answer for 12 of them, or I will grade your 12 worst. I mean, if you turned in 14 and 2 of them were perfect, I'm throwing those out.
How would that work for the online test?
What do you mean? What about the online test?
For the online test, doesn't it like make you answer everything before you submit it?
No, it asks you, are you sure you want to submit?
Oh, okay.
So and you say,
I think once you click a bullet point, though, you can't like.
Yeah, you can't undo it. So be careful.
Anymore.
Don't choose your answers until you're happy that that's definitely going to be one you're going to put in there. Okay, because yeah, if you click on one of the answers, say you click on C of question 13 or something, you're not going to be able to unselect it. That one's your guess now. So don't do that. It's kind of a pain because I'm doing electronically. It's a lot easier to do in person, but I am trying to make it helpful to you by giving you 14, choose 12. Oh, got another person came in. Any other questions?
So test number 6, we can work on that now, right?
Yes. Yeah, you can do it as soon as you want.
Okay.
I've got, you've got a practice test there, so you can take it a bunch of times and then wait till the last minute and do the practice test. I mean, take test 6, or you can do it now. Don't matter to me.
Okay.
The 242 class, they got 2 tests all of a sudden. Suckers. And they got a 45 question final exam they ain't asked me about yet. Suckers. I'm having fun at their expense. It's all good. All right, so we're supposed to start chapter 45.
That's funny though.
Go ahead, Tristan.
That's funny.
I know. I like to try to pick little battles between one of my classes and my other class and make them all think you're my favorite. I don't really do that, but I sort of pretend like I do. It's fun. I used to do it with my friend. He's a history teacher. So he was across the halls, and he doesn't believe atoms and waves exist. And I told him I didn't believe Charlemagne existed. So I think we're tit for tat. All right, so let's get started on chapter 45. It's getting near the end of the semester. Life is fun. Times are up. Remember, we don't have lab this week. We have optional lab, and you can attend any of them as I sent you the requests, the invitations, that is. So you're welcome to attend any of them, and they're just student-driven Q&A sessions. I'm not taking roll, all that good stuff. So come if you want. Or if you don't come, that's fine. And I usually stay there long enough where if someone can't get there right on time, I'm still there long enough. But once people have run out of questions, I sometimes will leave depending on how much other stuff I got to do. So with this chapter, it's called Astrophysics and Cosmology. And astrophysics is basically a descendant of astrology. Okay, so that's kind of weird, right? We know of, hopefully you guys understand that astrology is a pseudoscience. And pseudo means not. Okay, it means it's sort of one, sort of, but it's not. Okay, the problem was it was very much like a science initially, in that it had a lot of science stuff that you had to know to be able to play any part in it. So that was the founding of astronomy, was more or less astrology. And then it developed into, via the scientific revolution, it developed into a full science. And then the application of physics to that area of astronomy is the astrophysics portion of it. Whereas the just plain astronomy might just be the observing by itself, making the observations, but not necessarily understanding the laws that dictate the way things behave, not understanding all the physics. But you can, certainly you have to have a lot of physics to do some astronomy anyways. And then cosmology is a branch of astrophysics where we study the universe on such a scale that a individual galaxy, such as our Milky Way, which is 100,000 light years in diameter, is a point object. So if you can imagine stepping back in the universe so much that individual galaxies are infinitesimal, that's what you're studying when you're studying cosmology. You can get closer, of course, so you can study superclusters and stuff like that, or you can study walls and voids, and those are smaller fractions of the universe, but they're the biggest things in the universe. The wall and a void is just a huge open area where it appears to have very little, if any, galaxies at all. The wall, or a wall, would be sort of a two-dimensional lacing, if you will, of superclusters and galaxies that separate a void from something else. You can also have filaments or tendril type things that are long strings of superclusters of galaxies. And then, of course, you have the individual galaxies themselves, and galaxies you normally form into groups. And then those groups form together to make clusters. And then some clusters go together to make superclusters. And that's what you're studying when you're studying cosmology, and you're trying to make sense of it, how it behaves over time and stuff of that sort. So I'm going to start off with giving you a little intro to astrology / astronomy as it was done in Egypt, Greece, and Rome. Remember, those were the first civilizations, if you will. And by civilization, I mean people that no longer had to hunt and gather and amble about looking for their next meal, because they had understood the universe well enough that they could see there were times when the seasons would get cold and not be very precipitous, or not be very advantageous. Propitious was the word I was going for. Would not be very propitious to planting or picking food off the ground. And once you tie that in with the stars, then you get to understand how the calendar works per year, or a solar calendar as opposed to a lunar calendar. A lunar calendar is a lot easier to deal with because you're just keeping track of new moons or full moons or whatever. So you only have to count up to like 30, 31, something like that, maybe. Normally just 29, to be honest with you. But when you get to a lunar or an actual solar calendar, then you can actually have agriculture. And once you have agriculture, you're no longer subsistence. You're not living day to day just trying to find your meal for your family and yourself. You can actually have time to, say, develop art or develop music or literature. You can write things, you can draw things, you can study science, and you can let other people do the work that's necessary for you to live, i.e. get food together for you. And then you can use a bartering system, or even a fiduciary or financial system with actual money, monetized objects that you exchange for food. Once you get to that point, then you're a civilization that, like I said, allows you the freedom to study things that in some cases aren't what we consider most important, but in other cases it's sort of the most important thing. Okay. So it turns out the ancient Greeks were not bad. And in fact, the ancient Egyptians weren't bad either. By the time the Greeks come on the scene, we've already got 500-600 years worth of really good data on astronomy. In fact, we can tell now, for instance, that the Earth's axis is doing this on like a 22,000 year period. I might be misremembering that. I can't remember if it was 2242 or what, but anyways, it's not that important. It's something you can look up, but it's one of the things that we don't have to worry about with global warming, because it has such a long period. But at the same time, you do have to worry about it in terms of understanding how ice ages came about. Because that can combine with other factors all simultaneously to give you the coldest of the cold, and that leads to ice ages, for instance. But because that gyroscope type motion is so infrequent. In other words, it goes so slowly. You need hundreds and hundreds, if not thousands of years of data to see that. And the fact that we know that's really impressive because, we didn't get a telescope till the 1600s. So we've really only been studying science in a robust way for about 400 years. So 400 years is a pretty small time for us to piece together how stars live and die. When stars, for instance, even the shortest lived ones, which are the high mass ones, they live for at least 1 million years. So maybe 100,000 in the most extreme case, but pretty much 1 million years is how long they live. And we've managed to piece that together in 400 years. Is pretty impressive. But the ancient Egyptians would have used it. For instance, they named one star the dog star because it was the brightest star in the night sky. And it really is the brightest star in the night sky. It's called Sirius. And it actually turns out to be a double star. There's 2 stars in it. But Sirius is so bright that they thought that because they understood from the star motions throughout the year, they understood that the Sirius dog star, Sirius is literally a translation of a Egyptian word for dog. But anyways, that star was actually up during the day in the summer. And they thought that was part of the reason why the summers were so hot, was because that star, the scorching one, was so hot that even during the summer, it made the weather even hotter than just the sun. So by knowing that was really important. But what they also discovered about that star is that star happened to rise, what we call heliacal rising, meaning it rose just before sunset. It rose its heliacal rising on the same day as the Nile generally flooded. Once you've got that down, you're pretty golden. And he thought to himself, it'd be really nice if we had a star that gave us a warning, as opposed to just having, oh crap, the Nile's flooding right now. We got to go get our crops before they're ruined, that sort of thing. So what they ended up doing was they found another star that did it 2 weeks earlier, and they named that one Procyon, which Cyon's another word for the dog. So that's before the dog. And that's actually in the constellation Canis Minor, whereas the Sirius dog star is in the constellation Canis Major, which is the dog constellation. It's also the origin of the name Sirius Satellite Radio and why they have a dog as their logo. So that's some of the stuff the ancient Egyptians did. They had actually figured out correlation of the seasons with certain star motion, stuff like that. They had something called the decans, which were sort of basically the stars that would get you through the 10 hours of up to 10 hours of night. Basically, you could tell when one of those stars rose, that was roughly an indicator that such and such a month just started or something like that. Now, we were able to take that data that we had, and I'm sorry, I should have looked up some names. Hipparchus was one of them, but there's some names of some of the ancient Egyptians that kept catalogs. But when they learned that stuff, they started to look and see correlations, not necessarily causations, and they didn't really understand so well the difference between that, even though 3,000 years ago the human species is pretty much the same as it is now. So they're every bit as capable as we are mentally. They just didn't have the knowledge base that we had, and of course they have some knowledge base that we don't have now, so there's probably a lot of things they could kick our butts at. But either way, they didn't necessarily put together all the correlations, weren't necessarily causation. So they found, sometimes a lot of bad things happened when a person who was born on with the sun in Gemini, and when that person happened to have Mars in Gemini, that person might have died, or that person might have got married, it turned into a bad marriage, or that king who was born while the sun was in Gemini had Mars in Gemini, when he went to war and he lost. Okay, now they weren't very good at science, so they didn't know how to cut out the negatives and make sure they catch all the positives and catch all the negatives and stuff like that. So they didn't necessarily put it together, but that's how astrology grew. They thought that there was some correlation between what's happening to you and what's happening in the sky. So, and for instance, what constellation the sun was in the day of your birth was really super important. But because of that precession of the Earth's orbital axis, we've now figured out that precession was going on strictly because things like the Tropic of Capricorn, the Tropic of Cancer, They meant, for instance, the Tropic of Cancer. I believe that's the northern one. That Tropic of Cancer is basically called that because when the summer solstice occurs, the sun was in the constellation Cancer, and when the winter solstice occurs, the sun was in the constellation Capricorn or Capricornus, and hence we gave it the names Tropic of Cancer and Tropic of Capricorn. If y'all are noticing that I said that backwards, just make sure you correct it. Not that I'd test you on it, just that, you know, it's something I know, but I haven't, you know, I haven't taught astronomy in a long time, so I forget some of these things. But either way, the important thing is that's where they came from. Well, if you look now, they're not in that constellation. They're not in either one of those constellations, at the winter solstice or the summer solstice. And in fact, our original astrological signs don't match up anymore because of that precession of the perihelion, or excuse me, because of that precession of the orbital rotational axis of the Earth. That can combine, of course, with other things to make the Milankovitch hypothesis, which dictates what could actually, when we could actually have ice ages and stuff like that. But that was a good amount of data that the Egyptians could bring up with us. And then the ancient Greeks come along, and they are very curious bunch as well, and they build on knowledge. And in fact, they're the ones that sort of seem to take the step to say, maybe some things are knowable and aren't just due to the capriciousness of gods. They were very much a pagan group. Of course, the Jews were around at this time as well, and they were really the only monotheistic religion around, but everybody else was more or less pagans in the sense that everybody was believing in multiple gods. But it's kind of a cool time, and that's my what I consider the most interesting aspect of history is around the time of when Jesus walked the earth. You'd have cultures from ancient Egypt and their religions and their pagan gods still being worshipped and their practices still being carried out. At the same time, you had the ancient Greeks with their pagan gods, and then you ultimately even have the Romans who have assimilated a lot of their stuff and changed the gods themselves, which is why we have the planets named after the Roman gods. So for instance, instead of the planet Aphrodite that the Greeks would have called it, we call it the planet Venus, stuff like that. And that was pretty much how empires work. Empires absorb the culture and knowledge of the group that they take in. Obviously, they have to cut some heads off and get rid of some people and all that good stuff. But but they try to keep a lot of stuff because they know if the riffraff really gets together, they're pretty powerful. You know, if you get 300 million, 350 million Americans and they're upset about something, they can do some damage. So that's the way empires sort of work. They try to adopt as much as they could. When the ancient Greeks come along, though, they're not dumb. They're like I said, they're like humans, species wise, and they consider some things. They say, okay, well, if I take a block of metal, say, I can cut it in half, and then I can take one of those halves and cut it in half and keep on doing that. Can I do that forever? No, I can't. I don't think I can do that forever. So they imagined the atom, like I told you before, in elementary particles. So that was where we got the idea of the atom. A guy by the name of Aristarchus, Aristarchos of Samos, Samos, Aristarchus of Samos. He was living about 370 BC. He actually predicted the heliocentric model of the universe. And in this area where we're talking this history, the universe is pretty much the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and maybe 10,000 stars. All of which, by the way, when you see the stars in the night sky, they're all in our galaxy. You're not seeing any stars outside of our galaxy with the naked eye. So that's what the universe is to them. They don't think there's anything else, and that's fine. Okay. Now, Aristarchus did argue that the sun might be in the center and we'd be orbiting it. We don't know why, because there was this period, they call it medieval times, at least that's what my history instructor friend wants me to call it. I call it the Dark Ages. And the reason I call it the Dark Ages is because I made a timeline one time and looked up all the inventions and stuff that were going on from basically, probably 1000 BCE, before the Common Era, to today. And it's like all this stuff's happening, and then there's like nothing. And then all this stuff happens. That nothing period is what I termed the Dark Ages, and that's why many people have called it the Dark Ages, because basically science stopped. Well, it turns out during that time we were actually lucky, and this isn't some post 9/11 political correctness, as I've heard numerous people say. It turns out when this was going on, the Romans had now succumbed to Christianity, and they were that was the major religion. The Catholic Church was running everything, and they were really going out trying to let everybody know the good word, and they were destroying things that didn't look wholesome to them, and some foreign writing can look pretty creepy sometimes. So they burn a lot of that stuff, and we got a lot of stuff burnt that way. But during this time, the Arab and Persian type cultures of that era were actually building science. They took the science that had been created both by the Egyptians, the Greeks, and even the Romans. And the Romans didn't do quite as much as the Greeks did. They did considerably less, but they were more like an engineering group. So they were able to take a lot of the science and make luxury and nice things out of it. But still, the Arab culture of this time took over and built on that knowledge. And that's why we have now algebra and algorithm and sine and cosine. Those are all words from Arabic, basically. So, and in fact, they were the best navigators. In fact, Christopher Columbus navigator was an Arabic person, or a Mohammedan, as Thomas Jefferson would have called it. They called them the Mohammedans, meaning the followers of Muhammad. But they were the brilliant ones, and they saved a lot of knowledge. So we owe them debt for that. But that was the only real stuff going on during a big chunk of the Dark Ages, or the Middle Ages, as we say, or medieval periods. So the ancient Greeks, like I said, they come online. They have Aristarchus in 300 that does that. Then Eratosthenes comes around 200, 250, I think, BCE, and he's the librarian at Alexandria, and he's from Cyrene in Egypt, and he read basically in the Library of Alexandria that there was a place in Syene, S-I-E-N-E, I believe it is. I think it's modern day Iraq, where you could see all the way down to the bottom of a well at noon on the summer solstice, basically. And I think it was the summer solstice. Could have been the winter solstice, or it could have been the equinox. But the main thing is, he realized what that meant. That basically, here's a well like you'd see on Bugs Bunny, the type with the brick wall, or with the rock wall around the outside, and it's got a hole. Normally, you throw a bucket down there and pull it back up. This would just be an open one. Instead of having a little roof and the bucket to crank it up, it'd just be that open one. But when the sun shines all the way down to the bottom of that, that means the sun rays are actually shooting directly radially for the Earth. So upon realizing that, he realized what he had. So I'm going to go ahead and show you this in drawing form. So Eratosthenes made the argument that, okay, if I go out and measure a shadow on Earth at my location at the same time that this tunnel, or excuse me, that this well has light going down it, then what I know for a fact is the rays of sunlight are parallel. And if I happen to be down here, for instance, then I'm going to get a certain angle for my shadow. Let's say theta is on the order of 7 degrees. And it turns out that that angle happens to be the same as this angle, which is theta as well. So because of that, he can say, oh, well, 7 degrees is to this little distance, d, and he asks some travelers how far that distance was to Syene. That should be exactly equal to 360 degrees divided by the circumference of the Earth, where the circumference is the whole distance around. And from that, he was able to get a very accurate figure for the circumference, and therefore the radius, and therefore the diameter of the Earth, because the circumference is equal to 2 pi times the radius, or it's just pi times the diameter. And in fact, his value, Eratosthenes' value, and I'll have all these names written at the end, spelled for you. I'm going to put them on the worksheet after class. On the sheet after class, and put all the names on there so you can know who they are. Eratosthenes had discovered the radius of the Earth to a better degree than Aristotle knew it. In fact, Aristotle was off by like 40%, and he thought the Earth was about 40% smaller than it was. And in fact, had Christopher Columbus known the real value of that diameter of the Earth, then he might not even have petitioned to try to go and circumnavigate the Earth, because they didn't really have the technology to do so. In other words, the Earth would have been so big that if we didn't have a new world, they probably would have starved before they got around the other side. So that's kind of a neat happenstance, but that's the value they knew, and they went on. And yes, it's a common misconception that they were, proving the Earth was round. There was probably some, backwoods cultures that didn't know stuff like this, but all the upper echelon royalty and academics and stuff of those, they definitely knew the Earth was spherical. Now you might ask, how did they know that? Well, the ancient Greeks knew it, and we have their writings. The ancient Egyptians knew it too, but we don't necessarily have as much that tells us why we know about that. But what we know about the ancient Greeks is they actually drew or sort of pictured the moon like in 5-minute intervals during a lunar eclipse. If you actually did that, you could see that really what's going on if you say every 5 minutes, I'm going to take a photograph of the moon during a lunar eclipse. And then you put all those together, what you'd see is that, in fact, there's one big shadow in the sky and the moon's going through it, right? Because you could put all those pictures together and you could then see how big that shadow is. And it turns out, as the ancient Greeks did, they actually measured that to be about 2.5, 3 times the size of the moon. So that gave them some idea of what was going on. One, it showed them, of course, that the lunar eclipse was a result of the shadow of the Earth on the moon. But two, it showed them the shape of the shadow, and the shape of the shadow was exactly the shape that you'd expect if a spherical object cast a shadow on a spherical object. So that's how they knew that. Now, what they also realized is, hey, if I knew how much the shadow of the Earth tapered from getting from the Earth to the moon, then I could figure out the size of the moon relative to the Earth size, because it looks like obviously 2.5, 3 times, the shadow is 2.5 or 3 times bigger than the moon. Well, then they remembered, wait a second, during a solar eclipse, the moon blocks the image of the sun so that they're basically the same angular diameter in the sky, or the sun might be moderately smaller if we're at the right part of our orbit or whatever. But either way, what they know is only a very small swath of the planet gets to experience that total solar eclipse. Therefore, the shadow of the moon must shrink from the size of the moon, where when the light actually hits the moon, the thing causing the shadow is one moon diameter wide. But when it hits the Earth, it's almost infinitesimally small compared to the Earth. So they said, oh, well, the shadow of the Earth, just of the moon, just like the shadow of the Earth, evidently truncates or gets smaller by 1 moon diameter. So if you add 1 moon diameter to the roughly 3 times bigger than the moon that the shadow was, and you say, oh, well, the moon's diameter must be about 1/4 of the Earth's diameter, and that's pretty correct. So now you have the size of the moon as well as the size of the Earth. You can actually use versus first quarter, and you can try to measure very precisely the angle between the sun and the moon and on the Earth. And from that, that can allow you to use trigonometry and geometry to figure out how far away the moon is. Once you have the distance to the moon, and you know that it has the same radial size and angle anyways as the sun does, you can then, if you know the size of the sun, you can figure out how far away the sun is. So all this stuff they were able to do. They even considered the idea of the Earth orbiting the sun, or at least the Earth moving. But what convinced them that wasn't happening is that they reasoned, and this is really good reasoning. I'm looking at a lantern over there. Now, if I close this eye, I see that lantern is right there. But if I close this eye, it now looks like the lantern has moved to here. So it moves back and forth depending on what size of it. Now, if I go back to this eye, and this eye, and this eye, and this, it goes back and forth. So they reasoned that if we are moving, we should see stars that are closer to us moving with respect to stars that are farther away from us, and they didn't see any of that. So they made they said there had to be 2 conclusions. Either one, the universe is ginormous and we can't even measure how far the nearest star moves, or 2, the Earth's not moving. And they really just had a failure of imagination by saying that the universe couldn't be that big. In fact, we learned that the universe is really big. The nearest star to us is about 4.2 light years away, and that's Proxima Centauri. and that angle was so small, the ancient Egyptians and ancient Greeks, and even almost at the time of Brahe, they couldn't measure that size. Brahe could have measured it. So they did get rid of some, or they did really use some good logic, I should say, in trying to determine things. So that got us basically a geocentric model of the universe. Again, the universe, that small part that I told you about. And what they came up with was a model that looked like this. Now, they had to explain some things, so it became somewhat complicated. But one of the things they did was they say, okay, well, if I go out at nighttime on some time of the year, if I do it every year the same time, or if I do it several times over weeks and months, I will consistently see this shape of stars in the night sky. Okay, anybody recognize what that might be?
Orion's belt.
It does look a little bit like that, but it's actually Gemini. But that could be my drawing that made it crappy. This is like a mirror image of that. The only difference is one is a 90-degree angle and the other was an obtuse angle. That's how I find it. And then, of course, over here would be Cancer, and over here would be Leo, which looks like a backwards question mark. But anyways, if you see that shape, and then you see it next year, it'll look the same. And in fact, only because we had that data from Hipparchus and the ancient Egyptians that we know that these stars are actually moving relative to each other. Just like if you look at an aircraft flying over really high, it's a mile or two up above the Earth's surface, and it's going 780 miles per hour or something. It looks like it's barely moving. Well, imagine these things being light years away. They don't look like they're moving at all. So that was what they saw. So for that, they imagined a giant crystalline sphere. Whoa, evidently I'm going to spell crystalline with a CY instead of a CR. CRYSTALINE, sphere. And the giant crystalline sphere, they imagined was really, really far away, way farther than, for instance, the planets to us. And it had holes in it. And outside of the crystalline sphere was fire. And just like fire tends to flicker a little bit, that's why stars tend to twinkle or flicker, is you can see them through those little holes and you see the little flickering due to the fire. That was literally a working model of what the stars were, right? And if you see these stars as not moving, that's a perfect explanation. In fact, it's so good, we still use that giant sphere today. It's called a celestial sphere. And it's centered on the Earth, and we can use that in our astronomy classes to teach students how to figure out how the stars move day and night. Now, here's the weird thing. Every now and then, you'll look up in the constellation of Gemini, and there will be a visitor. There'll be, for instance, a star that's like right here. And it wasn't there last year, and it wasn't there the year before. And if you watch it for a couple of weeks, you'll see it move. And then it moves again, and it moves again, and it keeps on moving continuously. And then it starts to go backwards and gets really bright and really fast. It was as if this star came in and wandered through our constellation like that. And in fact, the Greek word for wanderer is planetos. So that's where we got the planets. The planets were the wanderers. They wandered through the constellations. So they couldn't be represented by a giant crystalline sphere with holes in it because they were moving all over the place. So what they put together, Ptolemy being one of the earliest people, Aristarchus did some, Eratosthenes did some. So we're looking at Aristarchus. That was the first person we talked about. Eratosthenes. He was the one with the pole. This is the guy with heliocentric. And then there was, I just lost his name. All right, Eratosthenes. No, he did that. There was another guy that comes along, And he's one of the first to really build a model of the solar system, which for them, again, like I said, that's the universe. But his model basically looks like this. You've got the Earth in the center. And there was a little bit of a problem in that Mercury and Venus never stray far from the sun. And this would be the sun. So what we knew was the smallest orbit, of course, was the orbit of the moon. So there's our moon right there. But then what we had was another orbit for Mercury, but Mercury never got very far away from the sun at all. So we had to imagine a line going from the center of the Earth to the center of the sun, and on which there was a epicycle. The center of it was on the deferent. So this thing is the deferent, this thing is the epicycle, and this would have Mercury on it. And that explained, of course, the fact that the star, that Mercury never deviated very far from the sun, because we'd always see it right along that little line, right? It would never be any further away than this. So that explained that. And it could also explain, while, when it did a loop like this brighter spot could be a result of when the planet got closer to us. So it explained double duty. And in fact, they had them for all the planets. Venus was also one that stayed near the sun. So its orbit would be like this. And then again, it had a bigger epicycle because it got further away. So Venus would be here, right? Then the sun's orbit was out here. And then, of course, you had Mars. But of course, Mars was on the epicycle as well. And you had Jupiter, and that was on an epicycle. And that wasn't, the epicycle wasn't to deal with being close to the moon. As you can see, they're free to move, but it was to deal with this loop-de-loop that it was doing. Okay. And then, of course, outside of that, we had the orbit of, say, Saturn. And that's even the reason we have the names of the days of the week that we have. I mean, you can tell, obviously, Monday is Moon Day and Sunday is Sunday. And of course, Saturday is Saturn Day. The other ones are a little more obscure, but they can be traced back to various languages to show us that, Wooten was Wednesday and Tuesday was Tu, which actually came from like Thor sort of idea. But anyways, that historical lineage is why we have 7 days of the week. But this was the Ptolemaic model of the solar system, and it was passed on from generation to generation as the way to do it, and it was a geocentric model. Okay, now these astrologers would make money, by advising the king on propitious times to make decisions, to get married, to go to war, all that stuff. And they'd also make money by creating almanacs. And the almanacs would be basically lists of certain months of the year where the constellations can be found, or in what constellation the stars can be found, the planets can be found, and that sort of thing. So every 5 to 10 years, they would have to go back, look at all the data they've accumulated since their last almanac, make a new almanac so they could predict where all the planets would be then, because that was very important to society. I mean, even today, for instance, Easter, if I remember correctly, Easter is supposed to be the first, the Good Friday is the first Friday after the autumnal equinox, after the first full moon. So the first Friday after the first full moon after the autumnal equinox is Good Friday, and then, of course, 2 days later is the Sunday, which is Easter. So even that hinges on the motion, for instance, of the stars, specifically when the Earth seems to cross from the southern, the sun seems to cross from the southern hemisphere of the celestial sphere to the northern hemisphere. So all that was valuable. And every year they'd have to go back and tweak it. And of course, they'd tweak it by changing the rate at which Mercury maybe goes around that circle, or rate Venus goes around that circle. Maybe they found that actually Venus drifts a little further away from the sun than they had originally say. So they make this epicycle a little larger. They would account for the most recent viewings of Jupiter and make sure this is set in the right location relative to the sun, as well as the radius of it being right and the rate of rotation being right. Same thing with Saturn and Mars, all that. And they'd have to do that every 5 years or so. And it would change a little bit each time. So it wasn't a perfect model, but it was, predictive enough where you could get results 5 and even 10 years out. And it'd probably be off by a little bit after even 20 years. But it was a complicated system. And then comes a guy named Copernicus. Now, Copernicus was really, he was a member of the church. He wasn't trying to be a radical or anything like that. But what he did was he gave us the Copernican revolution. And what that was he said, hey, we've lost our way. Aristotle taught us certain things, and we've lost our way from that. And for that reason, we need to go and throw this away and do something different. Because what had happened is Aristotle, who's of course a student of Plato, and Plato, who's a student of Socrates, Aristotle had taken basically huge leaps and explained a lot of nature for everybody. For instance, there was 2 types of motion. There was natural motion and violent motion. There were 4, maybe 5 elements. So the 5 elements, say, were earth, wind, water, fire, and the quintessence. Which you all know is Mila Jovovich. And the 8 people that saw that thought that was funny, I guess. So there's a movie called The Fifth Element, and Mila Jovovich played that fifth element. She wore like a almost like a bikini made out of a Band-Aid, really a small thing. But the other elements, the earth, wind, air, water, and fire, were responsible for the natural motion. So anything made of earth would want to travel towards the center of the earth, and that explained why things fell. And in fact, they fell in proportion to their weight. If you, for instance, set a log, which was somewhat earth, somewhat air, and somewhat water, if you set a log on fire, then the ashes from that log would try to float up, and some of it would fall down. The floating up would be the air part trying to get above the earth, and that was natural motion. And the water part was trying to get below the earth. That explained the parts that went down, and the earth part was trying to get on the earth. So these would be left there as well. Any other kind of motion where these things are not trying to get to their natural place was violent motion, and that required a force to sustain it. So if you wanted to push an earth thing left or right, you had to completely give it a force at all times. Obviously, Galileo fixed all that crap later, as did Newton, and explained it to us. But for instance, fire's natural place was like the sun, so it was up above the air. That's why smoke was rising, because it was partly fire. Wind's place, of course, is the atmosphere, so on and so forth. So he'd explained all that, and there were certain fundamental principles, and those principles didn't have to be proven because they were just obvious. And one of them was like heavens, the quintessence, implies perfection. And it's also unchanging. And the reasoning there is kind of simple and stupid, in my opinion, but it can't change because if it's changed, it changed from something perfect to something that was imperfect, which is unacceptable, or it changed from something that was imperfect, which is impossible, to something that now is perfect. So you can't change it at all. They also said, of course, in a very Sheldon-esque manner, that the perfect shape was the sphere. So since the heavens are perfect and the sphere is a perfect shape, all these things have to be spheres. So they literally imagine these things as being giant spheres. And then that's a giant sphere on a sphere. And that's sort of the reference they were making in A Bug's Life. If you ever saw that movie, you know that he was talking about, they were complaining about his tunnel in a tunnel plan. That's sort of making fun of the Ptolemaic model of the universe. So these were all spheres, and the only thing that's even close to a sphere would be a circle. So sometimes things were circles, but basically that was how everything worked. And by the time the Catholic Church is running things, they had all interpreted all those scriptures based on Aristotle's teachings. And because of that, that was a real big deal. Like if you say, no, the sun's not at the earth isn't at the center, why are things even moving the way they do? Everything's going to have to change. It's really problematic. But because of this, Copernicus was like, this is bad. We've now got difference and epicycles, and they even had equipoints. So they like put a point over here, and that's the point from which the rotation rate of this looked uniform. And all sorts of weird stuff. And he just said, this is nothing like what Aristotle taught us. So he did the right thing, but he did it, in my opinion, for all the wrong reasons. So that's why I separate the Copernican revolution from the scientific revolution, because Copernicus wasn't really being a scientist. He was basically, well, I mean, he was being a scientist, but at the same time, he was more appealing to authority. So what he did was he made a heliocentric model where basically the sun was here. And when he did this, the most natural thing was the fact that the period of Mercury was the smallest, was just a result of the fact that Mercury was the one closest to the sun. And the period of Venus being the second smallest was because Venus was second closest to the sun. And then the Earth, with its moon orbiting it, was third, and then Mars, and then Jupiter, and then Saturn. Okay, but he made them all circles. So this is heliocentric, circles, and constant speed. So that was the big deal that Copernicus brought to us. I just realized I don't know how to spell Copernicus. I don't know if that second letter is a O, a A, a U. Anyways, I'm pretty sure it's a O. But anyways, it's terrible. You've been typing so much you don't actually know how to spell words anymore. So he came up with this heliocentric model, and the church was okay with it. They were like, well, this is a much cheaper way for us to do our calculations. And in fact, it was just as good as a Ptolemaic model. So like the Ptolemaic model that was just getting ready to run out was creating things fairly accurately, but this was just as accurate. That was until a guy by the name of Tycho Brahe, and I've heard they pronounce it Tycho Brahe, who was a Dane. He was from Denmark.
Tycho Brahe.
Yeah, Tycho Brahe. I think that might be a better way of saying it. I don't know very many people from Denmark. I've only met maybe two in my life. But anyways, he's sort of the Russell Brand of the time. Okay. Well, at least in terms of his demeanor, he's a party animal. He loves to party. He loves to goof off and do crazy things. And in fact, Tycho Brahe is a pretty colorful character himself. He had what we would call a pet human, what they call little people nowadays. So he had that. He had a pet monkey. He once got a deer or a moose or something so drunk that it fell down the steps and broke its neck, sadly. He was a typical royal, and he was able to convince people to give him tons of money. But when he was in college, he had a fight over who was the better mathematician, and he got his nose cut off in the sword fight. And he had a prosthetic gold and silver nose that he stuck to his face with wax. He even ultimately died a painful party death in that because he's nobility. I don't know if you know this, but the nobles, for instance, the queen mum and the queen, they don't pee or poop, evidently. So Brahe could not pee or poop. So he sat there one day and ate so much and did so much that his bladder burst and he died of sepsis in a painful death. Not unlike the death of George Washington. That's the same way he died, except he wasn't partying because he was a cool dude. All right. Well, the big deal was he had a model. Oh, my throat just went dry. Hold on a second. So he had a model too, and he was trying to work it out. And his model was mathematically difficult, and he was running into problems, even though, you know, he already lost the fight about about being a better mathematician. So he really needed a better mathematician. Now his model was crazy. It was basically exactly the same as this, except without the sun there. So this whole thing, and then you put the sun over here and let that orbit the sun. That was Brahe's model. So it was absurd. It was just crazy. But anyways, he tried to work it out. In the meantime, a guy by the name of Johannes Kepler, who is the Mike Pence of the era, literally super conservative, you know, make sure he's never going to be in a room alone with a woman that's not his wife, that sort of thing. Well, he is teaching his class one day. He's a horrible teacher, by the way. He just like me, he gets all sidetracked on, you know, anything that interests him and just goes off as if the students aren't even there. And he did this one day, and he realized that the number of planets that we knew of, including the sun as part of that system, was exactly the right number for the perfect shapes or the perfect solids of nature to be in between them. So he immediately said, well, that can't be a coincidence. So he starts to build a model that's heliocentric, but has, you know, the perfect shape separating the sun from Mercury and Mercury from Venus and stuff like that. So he starts to work on his model, and he sends it to everybody he knows, one of which is Tycho Brahe. Okay, so he sends it to him, and Brahe's like, oh, wow, this guy's pretty bright. I could use him. So he offers him a job. Now, Johannes Kepler's a problem person in that he is like Mike Pence. He's so super conservative, super religious, really task-oriented dude, very, very hardworking, that sort of thing. He's also got like rickets and piles, and he's had shingles, and he had bad eyesight. He kept getting sick for various reasons. He was a wreck of a human being. Had no chance of being an astronomer, but he wanted to be, even though he couldn't see. Not only that, his mom, you know, being a widower, as often happened at the time, she had lost all her teeth, and you know that just looks creepy to men. So they would always accuse him of being witches. So he literally had to go back and defend his mom's not being a witch like 3 or 4 times. So he was acting as a lawyer, a doctor, a teacher, and a philosopher, and which was the equivalent of a scientist back then. So he had a bum deal. But anyways, he takes the job, and Brahe has his own little island called like 84 consonants, HVEEN or something. But he was given that island, and he could collect the rents. He was a horribly mean landlord, by the way. And he collect those rents and use those rents to create his lab. And his lab made the best observations and the best data that was ever made. And he didn't have a telescope. This was before the invention of the telescope. He had more or less like a giant protractor built into a wall, and a system where you could look along that protractor through a hole in another wall and see other stars and make, you know, good use of the time. And so he had the best data we had ever seen, and that data showed both of these were off. Okay, and it was really impressive what he was able to do. I mean, he's one of the first people that was proving, you know, where heaven was a debatable thing, because the heavens have to be perfect. So is the heavens just outside of the earth and the moon's perfect, or is it just outside of the moon and the moon's imperfect? And that was a line that occasionally moved from place to place. But what he saw was a comet that actually was closer to us than the planets, and therefore was proof that the heavens did change. He could actually measure that well with parallax, just like we were doing earlier with my left eye and my right eye. And he did other things. He was the first, one of the first persons to get really good data on a new star, a nova. It was so bright that you could see it during the day for like 2 weeks. But anyways, he had great data. Johannes Kepler gets there, is completely grossed out by his partying habit. Pretty much he sleeps till 2 or 3 in the afternoon, and then he gets drunk all day and eats, and, you know, loves on women and stuff like that all day and night. And then when night finally comes around, 8, 9, 10 o'clock at night, he goes out and works in his lab. And Kepler realized he was awesome at what he did, but he also saw that he was awful. I mean, imagine Russell Brand hanging out with Mike Pence, and you've got my story. You know, that's what I'm trying to say here. If you don't know who Russell Brand is, he's the guy that played Forgetting Sarah Marshall. He played in Get Him to the Greek. He was the guy they were trying to get to the Greek. He's sort of a stoner that in his biography, his autobiography was called My Bookie Wookie. He admitted that he was a sex addict and all this stuff. He used to be married to Katy Perry. Okay. So anyways, all that is sort of Russell Brand, Tycho Brahe character, Mike Pence living with him. Well, as I told you, Brahe one day's partying, his bladder explodes, he dies. Johannes Kepler complained that, he was so arrogant that he wouldn't even remove himself from the room long enough to keep from dying due to a burst bladder. But when he died, he went to the court. The family was trying to keep him from getting the data because they realized, like Brahe had, that Kepler might show him up. So he ended up winning in court. They let him have the data. So Johannes Kepler checked his model, didn't work. He checked the Ptolemaic model, it didn't work. He checked the Copernican model, it didn't work. So he had to start over anew. And in fact, he came up with his 3 laws of planetary motion, which you've already learned about in the gravity chapter, that basically the orbits are elliptical orbits with the sun at one foci. So that's like a bastardized version of a circle. That would have Copernicus and Aristotle rolling over in their grave. That they swap out equal areas and equal times, which meant they sped up and slowed down. That would have them both rolling in their grave as well. And that the square of the period was proportional to the cube of the semi-major axis. And those are exactly right. I mean, they really are right. And we find that's true everywhere. There are some things that it didn't quite cover, like the perihelion, the position where Mercury is closest to the sun. That actually precesses. It slowly moves around the sun like this. And you can figure out what that rate is. And Newton's laws of gravity does say that should happen, but they get a value that's wrong. It wasn't until Einstein came along with his general theory of relativity that we got the right answer. And that was one of the first pieces of evidence that said relativity was right, general relativity. So Johannes Kepler offers that, and he actually dedicates his book to Tycho Brahe. So he did have some respect for his mad skills anyways. So that was kind of awesome. Well, later we get to Galileo, where Galileo basically says, hey, I'm not okay with this idea of the church being okay with everything because it's just a model. No, I want to stick it right in your face and show you that they're being jerks. And I mean, he literally says, he calls Aristotle bad names. He asked one of his friends who was a cardinal, a high-ranking cardinal in the church, he asked him, can he write a book on the heliocentric model? He said, yes, no problem. Yeah, we would approve of that. That would work really nicely. It might be something we can use for our other people when they make almanacs. He's like, okay, so he writes the book, but he writes it as a dialogue, a conversation between an intelligent and curious but not knowing person, a person that doesn't know everything, a person that holds the position of the church, and a position that holds the position of Galileo. And the person holding this position of the church is named Simplicio, which is like sort of smacking him in the face. So luckily, in the intervening period from the getting permission to now, the cardinal that was a friend of Galileo's had become Pope. And he didn't pay much attention to it until people started telling him, Galileo is really making you look like an idiot. He's interpreting scripture. We got this letter he wrote a royal telling her that obviously that part of the Bible was meant to be a metaphor, because if it actually did that, the sun stopping in the sky, that would actually have the opposite effect of what God meant to do. So he was brought up before the Inquisition. He was showed horrible instruments that would be used to cut his entrails out of his scrotum. He had recently learned about Giordano Bruno being burned at the stake. So he basically said, yeah, whatever you want, right? Yeah. It's said that he said, yet it moves, but he was basically forced to admit that the sun must not move. And supposedly he said, yet it does, or something like that. But we actually have the transcripts translated to English at the in the what is the darn church in Rome? Anyone? Start with a V.
Vatican.
Thank you. I was getting all sorts of V words, and it wasn't Vatican. Yeah, so in the Vatican's website, you can actually look at all the transcripts of it, and it's pretty tight. But anyways, what data he had that convinced him was he saw that Venus had full phases. It had full moon, full Venus, half Venus, new Venus. You can't have that with this model. Right? There's no way you're ever going to get a full Venus, because the sun is what provides the light to Venus. And the sun is always on the opposite side of Venus from the Earth. So there's no way you get a full Venus. So him seeing that was a nail in the coffin. He also discovered the Galilean moons, which he called them the Medicean moons, which y'all can probably imagine why. And that shot away Aristotle and everybody else's complaint that how would anything follow along? You know, for instance, if a bird swept down off of a tree to eat a worm, he would be left behind. We didn't know that until Galileo come along, that there was this idea of inertia and that the bird would go along with the planet. But he saw in Jupiter 4 satellites that were staying with it. So whatever didn't cause them to do that is also the same thing that wouldn't cause the bird to do that. So he had that going for him. By the way, he did know of Brahe's model, and Brahe's model was perfectly fine with Venus. So Venus could have full phases in Brahe's model, but he ignored that. So anyways, he went to the Inquisition. They arrested him in house arrest, probably because the Pope was his friend. They forbid him from studying astronomy anymore. He went to studying motion, as we talked about in the chapter on Newton's first law of motion, which was Galileo's law of inertia. And that's the way he spent the rest of his life. In the meantime, we come across around 1920, we get the first experimental evidence by Edwin Hubble, who's on an observatory in Los Angeles, right? You've seen it probably on several TV shows. It overlooks Los Angeles, and he had the 100-inch telescope, a 2.5-meter telescope, and he was looking at nebula. And the plural of nebula is Nebulae. That's the plural. Some people say nebulas. That's okay, but it's technically nebulae. Is the plural. But these nebulae turn out to be, after Edwin Hubble comes along, turn out to be basically 3 things. Clouds, which is what the word nebula means, and that actually is the incubator for stars. So they get to maintain that name. So now when we say nebula, we mean nebula. We mean a cloud. There also were clusters of stars, and basically it was so many stars, they were so close together you couldn't see individual stars, so it sort of looked like a blur. Okay, so there's just bunches and bunches of stars. There's one, like I showed you earlier, right over this part of Gemini. There's a little triangle inside of a triangle that looks sort of like this. See that little triangle inside of a triangle? Right in there, there's a blurry spot. And that's the constellation Cancer, and that blurry spot is the Beehive cluster. It's literally hundreds of thousands of stars in one little place. And the third are actually galaxies. Well, he was looking at the Andromeda one. So Edwin Hubble looked at the Andromeda, which later became the Andromeda Galaxy, and realized this thing was really far away. In fact, we had a model now of the universe, and it was sort of like this grist mill with like an egg yolk in the middle. And we knew, you know, this was on the order of maybe 10 light years, 100 light years, maybe even tens of thousands of light years. But that was the biggest extent of any of this, and that was the universe as far as we had measured it. Well, because we had Henrietta Swan Leavitt, because we had her great discovery about Cepheid variables, she had found that Cepheid variables, their brightness goes like this. And if you find the period from here to here, you can use that to determine the brightness, the actual luminosity of the star. And since you know the luminosity, you know how bright it is. And it turns out that brightness is equal to luminosity divided by 4 pi times the distance away squared. So there's the luminosity. That's the total light that the star puts out. That's the sigma t to the 4th that you learn about in thermodynamics. And this is the brightness, and that's literally how many photons are landing on your camera. So if you have the luminosity and the brightness, you can immediately find the distance away. He used that to figure out how far the Andromeda galaxy was away. And he found the Andromeda galaxy. The data wasn't very good for Henrietta Swan Leavitt yet. So he found that the Andromeda galaxy was more than 100,000 light years away. Okay. It actually turns out to be 2.5 million light years away. And he realized it was the island of stars. That big telescope allowed him to see individual stars on it. And in fact, he saw a bunch more. And he saw, in fact, that if a galaxy, which ours is a spiral, by the way, the Milky Way galaxy is a spiral, and it's about 10,000, or excuse me, about 100,000 light years in diameter. We're about 26,000 light years out. So in about halfway out from the middle. If he found one twice as far away as another, it was running from us twice as fast as the first. And if he found it 3 times as far away, it was running away from us 3 times as fast. And he found also that if you went to another galaxy and measured the same sort of thing, you'd find that they would agree with you. In other words, everybody thought everybody was running from them. And if you were twice as far away, you were running twice as fast. If you're 3 times as far away, you were running 3 times as fast. And the only way we can make sense of that is that the universe itself is expanding. The space between the galaxies is expanding. It's not that the galaxies are moving fast through space, it's that the space itself is expanding. We, as our little solar system, for instance, are only moving about 200 meters per second, so that it takes us about 250 million years to make one trip around our galaxy. These things are moving in excess, in principle, they could move in excess of the speed of light, but it's not a problem because it's not that they're moving, it's that space is growing that fast. That was the experimental data that forced us to agree that the Big Bang must happen. And I want to get into you and make sure that you understand this. The idea of the Big Bang is not that space was here. And I know we're time's about up, so if you need to leave, go ahead. I'm just going to finish this off a little bit. The Big Bang is not that the universe, all the space was here and there was nothing else. And then at one point, some point in space exploded and a bunch of matter came out. That's not the Big Bang. That's what a lot of people think is the Big Bang. That's not the Big Bang at all. The Big Bang created the universe. So what is the universe? Well, that's all the matter. That's all the energy. That's all the dark matter. That's all the dark energy, which we haven't even talked about yet. And that's all of the space itself. All of that is the universe. So the Big Bang created the universe. There was no empty space here. There was nothing that we know of. And that's why, for instance, when this was postulated as a theory before the experimental evidence came in, it was postulated by a guy by the name of George Lemaitre, who was a Belgian priest. The Pope was like, man, this is awesome. This is the bona fide proof of the book of Genesis, right? And of course, Lemaitre's like, no, don't do that. What if the experiments come back and they're going to make you look like an idiot because you're the Pope and you just said something's got to be the case. So there it's God, right? So he said, yeah, don't do that because something bad could happen. And it will look terrible. But anyways, it's kind of neat how we hear today that, Big Bang is the from the depths of hell and Satan put it on us and stuff like that. No, it was actually introduced by George Lemaitre, a priest. So this Big Bang really is the universe being created out of nothingness and not expanding into anything necessarily, but the space itself is getting bigger. At one point, it was smaller than the nucleus of an atom. And this guy, Ralph Alpher, is a grad student working under George Gamow. He does all these calculations and predicts that if this is the case, there should be this much hydrogen, this much helium. He actually used the data of those 2 elements, but then he predicted how much lithium and beryllium and boron there would be. And then he also predicted that we would have a radiation that I'll explain a little later coming from everywhere that sort of acts like something at 2.7 Kelvin. And lo and behold, that was found. And he predicted that the universe would be expanding exactly like Hubble did. So that was how we got the Big Bang. And if someone asks you, for instance, where the Big Bang occurred, you say right here. And if you're somewhere else, you say right there, because it happened everywhere. If that first case of the Big Bang was true, you could trace the lines back of the velocity of all the galaxies, and they would all come back and hit at the same point in space. That's not what happens at all. everybody feels they are the center of the universe. It's more like we blew up a balloon about this big, and then every centimeter we drew a circle around it, and then another one above it, and then another centimeter above that, and then below that too. And then every centimeter we put a dot, and each one of those represents a galaxy. And you say, okay, well, this one's 1 centimeter from this galaxy, and 2 centimeters from this galaxy, and 3 centimeters from this galaxy. Now you blow it up till that first and second are 2 centimeters apart. Well, if that first and second are 2 centimeters apart, now that second one's now 4 centimeters apart. And if you calculate how far they move twice as far in the same amount of time. And that third one moved 3 times as far in the same amount of time. That is the accurate prediction or picture of what's going on with the Big Bang. It's a balloon expanding. And this, we don't know anything about there being an inside. We're just saying we're like the outer rim or the outer latex or rubber portion of the balloon. So that's it, folks. We will finish up chapter 44 next time, but I've gotten you up to the Big Bang and understanding where that came from, and we'll go into the rest of cosmology, Hubble's law, Ralph Alpher, George Gamow, nucleosynthesis, and all that good stuff. Thanks for coming. I'll wait for the last person to leave in case you have any questions.
Thank you. Thank you.
No problem. Thank you. You're welcome. Anyone?
I was going to say I read about Tycho Brahe, and he is quite hilarious.
Isn't he?
I know I found that quite humorous when I read about him previously.
Yeah, someone wrote a biography a couple years ago, and I got to read that. That was pretty interesting. And yeah, he's a cool character, but he's also kind of a weird character.
He's a fruitcake.
Yeah, and actually all of them are. I mean, heck, if you look at what what Kepler believed, he believed like in all sorts of crazy things, like the sun was giving us superpowers and stuff like that. There's a lot of weird theories of the time, and like Newton believing in alchemy. Basically, there's some way to turn gold into silver, or excuse me, lead into silver or lead into gold or something like that. And there was an elixir of life.
Well,
yeah, we can do it now. It's just more expensive than it's worth.
Yeah, it's just it would take too long. I think it requires firing electrons at lead, and it has to absorb it up before it goes through enrichment in a way.
Or neutrons or protons or something like that. You can actually,
I think it was
you can force gold to turn into it, but it literally takes more expensive energy than the difference of the cost of the lead and the gold. So yeah, nuclear physics is the way.
All right, see ya.
I hope you enjoyed it, Tristan. See ya.